Thanks for attending this presentation, Snack and Learn, WSP, on how can the sustainable materials and construction methods help to reduce the embodied carbon of the buildings we design. So, I'm Dan Hagan. I'm a structural engineer, a director, and as well as that, modern methods construction lead for properties and buildings for WSP in the UK. I have a team of circa 8 engineers who work in my team, and we work in normal delivery of normal projects, but as well as that, we try to put a slant of MMC on most of our projects. And as well as that, I also look after the wider kind of MMC within properties and buildings, so the MEP systems and also the facade systems. So the agenda for today's talk: why should we design using sustainable construction materials? What are mass timber construction products? Gives the game away slightly there. Optimum use of the material. I've got 4 case studies to go through, a short summary, and then we'll go through some Q&A at the end. So why should we design using sustainable construction materials? So construction materials are responsible for 40% of the materials used today, and they account for 11% of global CO2 emissions. If concrete was a country, it'd be the 4th biggest polluter or emitter of carbon in the world. It's also the 2nd most used material after water. As globally, there's a climate emergency, and timber is the only sustainable construction material available. In terms of where do these sustainable construction materials come from? Where do they fit? In the UK, we've categorized types of modern methods of construction, and remembering that steel is probably one of the first types of modern methods of construction. So those are categorized into 7 different types, 1, 2, 3 being structural materials, and 4, 5, 6, and 7 being non-structural elements. So 1 being volumetric modular construction. That's either a turnkey solution or a chassis, and that could be a hot rolled steel chassis, cold formed steel chassis, or could be a cross-laminated timber chassis, for example. Panelized construction, precast concrete, timber SIPS panels, cross-laminated timber walls, LVL walls and slabs. 3 being, like I said, structural steel elements, pre-manufactured off-site, brought to site and erected. Also Glulam elements in beams and columns. And then 4, 5, and 6. 4 is 3D printing of structural elements or non-structural elements, for example, components in construction. 5 is things like kitchen, bathroom pods, so in some respects non-structural volumetric modular, as well as that pre-manufactured servicing routes. 6 is optimized construction processes, large format cladding systems, for example. 7 is innovation on site, so robotic laying of brickwork, or digital twins of buildings, so that maintenance can be undertaken in later life more simply. And then if we look where modern methods of construction sit into the procurement process within the UK, the UK government released the construction playbook, which plays heavily on the principles of modern methods of construction and also the early engagement of stakeholders and also the supply chain, which leads to a platform construction system, always developing from a kit of parts, utilizing those elements, repeatability, etc., will drive down cost. And where does our commitment to net zero fit inside of this? WSP are going to halve the carbon footprint of our designs and advice by 2030. And in doing that in the UK, we're taking on the principles of the London Energy Transformation Initiative, taking on those 6 principles: build lighter, build low carbon, build collaboratively. And collaborativeness is particularly important for MMC, like I said, getting the supply chain involved at a very early stage 1, stage 2, for example. And what we did in 2020 was undertake a review of nearly 100 of our projects over 12 different sectors and all of our UK offices to work out where we sat in terms of our cradle to construction levels of embodied carbon. and on the right hand side here we've got the kind of LETI 2020 requirements, and we've got the LETI 2030 requirements. So for non-domestic projects, 600 kilograms of CO2 per meter squared versus 350 in 2030. And at the bottom here we're identifying structurally what that means in terms of the structural materials of the development. So you can see in most cases we were there or thereabouts, although on some projects, there was quite a bit to go, but obviously we're working towards it. So what are mass timber construction products? So mass timber construction products are all derived from sawn timber elements that you can buy from your local DIY shop, planks, joists, etc., which are then post-processed, whether that's a full manufacturing process or whether that's an artisan gluing process, into larger structural, stronger products such as Glulam, cross-laminated timber, LVL, and we'll look at each one of them in the next couple of slides. So Glulam are sawn timber boards pressure glued to form larger structural elements, and they're usually used as beams and columns. They come in grades from GL24, which is akin to domestic grade timber or high strength domestic grade timber, 24 being the newtons per millimeter squared or the bending stress capacity of the element, up to GL36 being a very high strength material. Produced in either homogeneous or combined grade, homogeneous being that all of the element is formed from C24 timber, combined is the outer elements of C24, the inner core of the element is potentially a lower grade. Depths from 80 mil to 4 meters, widths from 60 to 280, and then block bonded together to make much wider elements, lengths up to 40 meters. In fact, I saw on LinkedIn the other day 42 meter beams were being delivered in Australia for a project there. Various different species of timber available, larch being the only one that you can use in service class free being an external environment continually wetted, for example a canopy structure. Different types of grades in terms of where it's produced. This is quite European focus, so Europe, but we can also produce it in the UK, and I'm sure in Canada and North America there are similar facilities. Cross-laminated timber, sawn timber boards bonded in single layers arranged at right angles to one another in a minimum of 3 layers, either a wall or a slab, produced again in domestic grade timber, high strength domestic grade timber C24, sections from 60 to 320 deep in 20 mil steps. Widths is 2.95. You can get larger widths and smaller widths. However, it's all based on a kind of automated production line. So that kind of sets the width of the element, and then the length is dependent on where they cut it, but could be up to 16 meters for a transportation, for example. What species? Spruce, different types of surface quality, mainly produced in Europe. However, there is some future funding to put a factory in Scotland. And then laminated veneer lumber, you could look at this as like maxi plywood, multiple layers of 3 mil veneers bonded together to create beams, columns, walls, studs, and slabs. Essentially, just peeling a log like a toilet roll in some respects, and bonding each layer together. So you can see there that the beam and column elements can be twice as strong in some respects as the lowest grade Glulam system, which makes them more expensive, obviously. In terms of the panels, they're made in panels of 2.5 by 50 mil wide, 2.5 meters deep, by 50 mil wide, and they're block bonded together to create much bigger elements, beams and columns, etc., up to 24 meters, usually non-visual, usually spruce, and mainly produced in Europe or Canada, for example. And then you get combinations of those products. So you can get ribbed panels which span further, for example, than standard CLT slabs. As well as that, they give the opportunity to service within the voids of those elements. So that was that. And then what's the optimum use of the material? Where are we seeing the optimum use? So in the UK, in the last couple of years, we saw the use of CLT extremely prevalent in the production of residential apartments up to circa 15 stories. That's probably at the moment about the kind of limitation insurance-wise for the material. However, there were changes in the building regulations due to a catastrophic fire in a building in central London, which meant that you can't build the external facade of a building greater than 18 meters with a combustible material, which meant that we need to think about new uses of this material. So therefore, what we went to our clients and said, you know, we're developing commercial offices for you. We understand you've got ESG and sustainability targets. Why don't we look at a small change? So why don't we change the composite deck slab in a steel frame to a CLT slab? And in doing so, keep the same grid spacings that you would expect if it was the composite deck solution that you had previously. Keep the same potential for servicing through cellular openings in the beam that you would have if it was the composite deck solution. The design life is the same. The potential for fire resistance is the same, and we're optimizing the panel based on the grid to ensure that when we're transporting the material from Central Europe, that we're utilizing the most amount of timber inside the back of a trailer as opposed to air. So, for example, trailer can transport circa 260 square meters of floor panels if they were 160 thick. So, how we've been doing this in terms of our option studies at stage 1, stage 2, reviewing the material or the construction type against more traditional types of solutions, and understanding or promoting the fact that yes, the CLT might be more expensive than the composite deck solution. However, there are other benefits, such as there are less material deliveries for the CLT hybrid, which are particularly important in congested city centre sites. The embodied carbon taken into account the sequestration is circa 2.5 times less for the CLT hybrid solution. And especially in terms of program, the CLT hybrid is the lightest solution, so therefore the substructure will be the smallest of the three. Sorry, just bear with me. And then if we look at the erection of the superstructure, erected in the same period of time as it takes to place the composite deck via the shear studs. However, then in the concrete solution, or the composite deck solution, sorry, you have got to lay the reinforcement, pour the concrete, allow it to cure before you can traffic it. So therefore, the CLT hybrid is erected the faster and therefore opened the soonest. So those are the kind of differentials that you wouldn't necessarily realize for that solution. So I'm going to go through 4 case studies. So the 4 case studies, starting first with Grand Union House, which is a retrofit project, working with Seller, the client who developed the shard. 6A are the architects, and we are providing multidisciplinary services on this project, and we are just getting towards the end of stage 3. So this building is located in Camden. It's directly behind the Grimshaw listed Sainsbury's supermarket there. And this, in the top right-hand corner here, is what the building used to look like before it was recently renovated to this beautiful building that I'm about to show you now. So this lovely building here is going to be completely renovated. At the moment, it comprises a car park grade, offices above, and also a car park to the Sainsbury's supermarket below. So it comprises a reinforced concrete frame, and then on top of that is a steel frame roof structure. What we propose to do is to remove the existing roof and undertake the following refurbishment, which is 3 stories of CLT hybrid, additional accommodation, the infill of the ground floor in a similar construction. And in doing this additional work, what we were able to do was we did not need to strengthen the existing columns down between level 1 and basement. and neither did we need to strengthen any of the foundations, which, as we didn't have access or ownership of that and that space, and also it needed to be operational for the supermarket, that was, you know, extremely beneficial for this type of construction. As well as that, we shouldn't ignore the embodied carbon. From cradle to construction, 140 kilograms of CO2 per meter squared, and the whole life at 35 kilograms per meter squared, incorporating the sequestration. That's what the building will look like in the future when it's fully clad, and you know, you can't see the timber, shall we say, or at least you can see the soffits of the slabs. So this is the second case study. This is a 12-storey office located on the banks of the Thames, and it is currently at stage 3. We are providing full multi-disc services too, and this is the planning solution that we had, that we took to planning in 2019. I think we got approval for this scheme, and it was based on a 270 PT slab on a steel vertical structure. It had lots of internal columns because of the span of the PT system. As well as that, we had to bridge over a Thames water trunk sewer, which ran directly through the site. So in terms of embodied carbon, 210 kilograms of CO2 per meter squared, quite a lot of GGBS in those mixes, quite heavy loads on the substructure because of the kind of heavy construction that we're proposing here. Anyway, our client, the planning scheme, sold the site to a new developer who wanted to make this their marquee development in London. It's their second development, and they put quite stringent sustainability criteria on the development. First one being that the embodied carbon should not be greater than 500 kilograms of CO2 per meter squared, and also the operational energy should not be greater than 55 kilowatt hours per meter squared. So what we did is we proposed the CLT hybrid solution, which meant that we reduced the number of columns. We had a single line of columns, which removed the requirement to bridge over the trunk sewer. We had 50% less embodied carbon, 75% less deliveries. Substructure loadings reduced significantly, so therefore the program for construction reduced significantly too. So this was a new type of construction for the client, and they were very keen for it to work for them. So as well as that, what we did is undertake some upfront analysis that we may not have necessarily done until later on in the process, to prove that this type of construction was very similar to what they were used to. So we undertook a vibration analysis to understand the response factors of the floor plate, and as you can see here, we were at worst case up at mid-6s, but in a lot of areas, you know, happily satisfying the requirements for an office. We also gave them an understanding of what needed to happen in terms of acoustics to achieve a kind of UK standard for offices. You know, the CLT slab is lighter, less mass. So therefore, we applied a 25 thick screed board on top of the slab to get it to perform akin to the BCO requirements. We also advised them via the Structural Timber Association Volume 6 Fire Safety Flowchart on the kind of routes to compliance for this type of building. As I said, it's 12 stories, so therefore it was above 18 meters. And what that meant is that we either need to encapsulate the elements, which we don't want to do because we want to be able to see the slab. So we either need to undertake an auto extinction calculation, which our fire engineers at WSP can do, or we needed to undertake a full-scale fire test. And there's lots of buildings that have gone through this process at present. Lots of buildings within the industry that are being built from this type of system. So therefore, we're lobbying for the industry to share this data so that, you know, route to compliance and understanding within the insurance industry, and also the fire brigade is eased, and these types of buildings can be easily assured through that process. So this third case study, just take a drink. is a major project. This is 1 million square foot of office space with a 250 key 5-star hotel built on top of that. The first floor of the office space, or the first floor of the amenity level to the office space, is circa 30 meters above ground, and there's a 4-story transfer truss which bridges over a major infrastructure hub with lots of buried people movement assets below the site, and also a listed element as well. So that kind of transfer structure set the grid at stage 1 for the construction. And therefore, what we did is we explored the alternatives in grid spacings and also alternatives in construction types. So various different grid spacing here, and then different construction types. So first one is the CLT hybrid, and then the second one being, can we incorporate more timber in the solution, i.e., LVL secondary beams. So this is a comparison study. Top elements being the composite deck solution, and this line here being the LETI 2030 requirement for the slabs and beams of a superstructure, circa 137 kilograms of CO2 per meter squared. And as you can see in the CLT hybrid solution, the kind of sweet spot for the grid was 12 by 9, and obviously reducing further and further down, we are reducing the embodied carbon. And obviously, the more timber elements we have in structural system C, the more we move towards a carbon neutral solution when we take into account sequestration of the whole life cycle. However, following that study, we then had a review of the structural zones, the floor to ceiling. It's obviously 1 million square foot of office space, so therefore there was quite a large distance from the center of the building to the windows. So we wanted to maximize the floor to ceiling. So what we did is look at incorporating the structural and MEP zone together, and utilizing a UFAD system, place the CLT on the bottom flange, holes through the beams, and pushed air from the risers out. And in doing this on a 12 by 9, we had 95 kilograms of CO2 per meter squared. Whereas if we would change to a 9 by 9 grid, we reduce that by 10%. And then if we change to the 7.5 by 7.5 meter grid, because we'd squeezed the floor zone so much, we had quite heavy beams, quite heavy shallow beams. So we actually increased the embodied carbon. So if we look at this is a kind of summary of all the various exercises that we undertook. And on the left-hand side here, you've got the kind of project LETI target, the structure LETI target, and therefore the superstructure LETI target of 168. And you can see the different varying grids, the different types of construction. For example, the CLT deck on a 9 by 9, 88 kilograms of CO2 per meter squared with 80 kilograms of CO2 spare, whereas 7.5 on a full timber option would have given us only 41. So the final case study is long span structures. This is also another area of growth that we've been looking at, in terms of the fact that throughout COVID, none of the shops were open, so everybody was buying everything online. So all of that stock needed to be stored in big warehouses. So working with a major developer of these warehouses for tenants, we undertook an exercise, and they undertook their own exercise in terms of WSP. Did a whole life cycle carbon exercise for them in previous studies to identify how much carbon they were producing via each one of these developments, and in doing so, they therefore then put that back into a fund to make sure on the next ones that they weren't emitting as much carbon as they were. So this is a 40-meter span portal frame, 26,000 square meters of warehouse. So what we did is we undertook a stage 2 exercise where we looked at the portal frame that had been designed by another engineer, and we proposed alternatives in mass timber construction. So the portal frame, steel portal frame, was circa at the time, and I'll say that's at the time because that was something like February last year, and it's definitely more expensive now. It was about £20,000 for the portal frame per frame. bowstring truss solution here had a 1200 top chord and a 85 diameter bottom chord, and that was circa £30,000. We also gave them an option for a tapered beam solution where we had a 1200 by 2.5 deep tapered beam. And then we gave them another option where we incorporated an internal column, which actually brought the numbers or the cost in line with the portal frame solution. And then also, as well as that, we looked at the office structure in CLT on a Glulam frame. We also proposed the purlins for the sheeting rails and also the roof coverings in Glulam. So this was a stage 3 design that we came up with, a bowstring truss solution. We've incorporated steel bracing in the roof and in the elevations, but there's no reason why that couldn't have been Glulam too. So this is a sustainability or a whole life cycle carbon analysis of the baseline, which is the portal frame solution, identifying the kind of carbon hug of each of the elements. And you can see that the kind of structure takes up circa 30% of the requirements. However, things like the internal enclosing walls are up at nearly 30% because over the whole life cycle they will need to be replaced after 20-25 years. So this is a review of the various different solutions, and what you can see here is that you have got the baseline at 1,721 tons of CO2, and by incorporating all the different solutions that we gave them, so GGBS in the concrete elements, the Glulam frame, the Glulam office, and the Glulam bracing and roof purlins, we were able to reduce the whole life cycle carbon by circa 30%, and that didn't account for the sequestration of the timber either. So if we incorporated that, we would have been much further down the line. So in summary, this type of construction or these type of modern methods of construction work based on successful and strong relationships with the supply chain. So understanding those relationships, understanding the key players and talking to those people early is very important. As well as that, advise your client early of all the key items to de-risk works later. For example, make sure their insurers are on board with this type of construction, make sure they understand the requirements of fire and that a full-scale fire test may be required. Use the material to its optimum use, and in combination with traditional materials, especially the reuse and recycling of steel, because virgin steel is very carbon heavy, and that can skew some of the numbers for example the CLT hybrid solution. As well as that, using the columns in steel as opposed to timber, because the timber columns will become quite large if you've got large or tall buildings, and it's not necessarily the best use of the material. And then project teams and clients to share fire tested data with the industry, and that's what I was talking about earlier about collaboration as a whole. This industry and engineers, architects, clients, if we want to get to net zero, we want to get on this this climate emergency trail, we need to start making these types of buildings easier to assure and accredit. And that was it, a bit longer than I should have done there, but hopefully there's some questions.
Thank you, Dan, for your presentation. We just have a couple of minutes for just one or two questions. So you can still log your questions in the question box on the GoToWebinar platform, and also Dan's presentation is available in the handout box. I will start with the first question. What experience do you have with regards to recycling or reusing steel elements?
Yeah, so my colleague David Laversia and Diego Padilla Phillips, they have been speaking with the European Metal Recycling, and I might have got that wrong, authority about recycling the structural steel work that comes off building sites, because at the moment it doesn't necessarily go back into the steel production process, it goes into manufacturing of other things, shall we say. So we are working with them, and if you're in WSP, there is a TRM on that I can point you to after this, that explains what we're doing there. But as well as that, lots of the the kind of steel fabricators or steel production facilities are on board with that too. So people like Nucor in North America are doing that, and ArcelorMittal are also doing that in the Europe area, and they're obviously in America too.
Thank you. Next question is there enough land to grow all the timber to replace all the steel and concrete we currently use?
So I suppose that's more a question about timber, because people do wonder, if you're using all this timber, aren't you just destroying lots of forests? And the answer to that is no, because all of these forests are sustainably managed. And if you were to go on any of the producers' websites, for example, if you go on Stora Enso's, it explains how they manage and replant and regrow trees, and how much of the forests that they have, and how much they're actually harvesting per year versus how much they're actually planting that year. And for example, Stora Enso, these building products are actually quite a small percentage of what they're actually doing. They're more into packaging and such like. So yeah, there is lots of sustainably managed forests in timber. In steel, we need to move towards recycling these materials more readily. Especially as we've got so many buildings that need retrofitting, or buildings that can be demolished and parts of that building reused. Concrete is probably the only one that you can't necessarily properly recycle, in that you could crush it down and you could use it for some other material in the construction, or you could use it for crushed aggregate inside concrete mix. You might be able to separate the cement. I'm sure that people in the universities are looking at that, and obviously byproducts of the steel industry like GGBS, pulverized fuel ash, etc., are used in the concrete industry to make that a more sustainable product. But the only renewable product, the only one that grows, is timber.
Thank you. I will take the last question. What is the carbon offset payment based on? For example, is it just a total carbon, or is it relative to a benchmark?
So the Green Building Council, as far as I'm aware, the carbon offset payment per ton of carbon is 95, or it's a guidance figure more than an actual stringent figure, but it's at 95 kilograms per ton, I think. I'd probably have to check that, and it's probably better if I ask my colleague David Laversha on that one.
Okay, no problem. Thank you. So thank you for all the questions. We have additional questions that will be answered directly via email by Dan. So thank you again, everyone, for joining, and thank you, Dan, for a fantastic presentation. Feel free to follow up directly with him via the contact details shown on the screen. And that's it. I will wrap up the webinar today. Thank you again.
Cheers. Thank you. Thanks for listening.